Hi everyone, I hope you're doing very, very well. My camera has just randomly died, so you'll have to forgive me for not seeing my beautiful face today, but I'll try and get that one figured out in a second, try and work out why it's died, but it seems to have done so. Anyway, I hope you guys are all doing well. I hear you've been up to your doing your mocks for a second time, so hopefully that's been a worthwhile exercise for you. Do by all means say hello in the comments. It'd be great to welcome you in. I can see there are a few of you there already. So I'm going to crack on without any further ado and get into memory and storage and think about numbers, which is the next area that we are going to cover. So I think first of all, just thinking about really what's involved here. So first of all, we've got the idea of units of storage, that's bits, bytes, megabytes, all that kind of stuff. And then about converting from denary to binary, from binary to denary, about adding binary numbers, and then doing some conversion to hex. And then we'll look at binary shifts and think about how we can calculate the size of text files, and then look at characters and see what character sets are and where they fit into the grand scheme of things. So that's kind of where we're going to go today, and I'm going to get through, I should get through all of this in, I reckon, about half an hour, 40 minutes. So that is the grand plan. So we'll jump on with a 20-minute teach, and I will try and get my camera to actually behave, but we'll see. If it doesn't come, it doesn't come. It doesn't really matter. But it's typical that it literally died about 10 seconds before hitting the go live button. Right, so let's start from here. So imagine yourself, you've done the first couple of pages of your exam, you've got to page 2 or 3, and it's going to ask you a question like this: why do computers use binary? And this notion of binary runs throughout this entire module, or throughout this entire topic. And why is that? Because they want you to understand that whether you're looking at an image, whether you're listening to a sound, whatever is happening, fundamentally it's all binary, because that's all that CPUs are able to understand. So in the first part, they will ask you, and there'll be a 1 or 2 mark question on this, and they'll ask you, why do computers use binary? And so what you can do, you can go 2 ways with this. You can say, first of all, that think about what computers are actually made of, is that computers are made of transistors and circuits, and they've got 2 states, one which is on and one which is off. And that is really easily represented in binary, with 1 being true, being on, and 0 being off. So you've got 2 marks potentially there. One to say that computers have got transistors, which only have 2 states, and that those 2 states can be easily represented in binary, because binary also only has 2 states, both on and off. So that's a nice, easy way to sort of lean into this particular topic to make sure you can get some good marks at the start. So just rehearse the fact: computers are made of transistors and circuit boards. They've got 2 states, on and off, and that's easily represented in binary. So there's your first couple of marks on the board before we go any further. Now this next part, the units of data storage capacity, which is a ridiculously horrible phrase to have to repeat, this is what we're talking about. And I wonder if that very first item that you can see there is one that you actually recognize. And that is that the smallest item of the smallest unit of data storage is a bit. And a bit stands for a binary digit. A binary digit. See, clever, isn't it? B-I-T. There we go, bit, a binary digit. And that's got one of 2 states, either 0 or 1. And then you increase 4 times that, so 4 bits is what's known as a nibble, and you can see this notion of food running throughout this, well, up to a point. And then after that, you've got 8 bits, which is known as a byte. Now, once you get past that, you're then into the units of data storage capacity that you're aware of, because you've moved music around from your phone to your computer, or because you've downloaded games. So you kind of have a sense that you've got kilobyte, megabyte, gigabyte, terabyte, and petabyte. And of course, although it says 1000, it's actually 1024. You get a mark because in binary it's 1024, not 1000. But you'll get your mark for saying 1000. So frankly, I would just stick with that. So what you need to remember are the first 3. And then the rest, you just need to know in which order they go. And they will get you to do a bit of maths between it, maybe turning a number of bits into a kilobyte, or vice versa. And it should be fairly straightforward. So if you think about it, A bit is either a 0 or a 1. It's the smallest unit of data storage capacity. A nibble is 4 bits, a byte is 8 bits, a kilobyte is 1,000 bytes, a megabyte is 1,000 kilobytes, and so on. So once you get down to kilobytes, it's actually quite straightforward. But then you do need to know the first 4. So they may well ask you to do a bit of conversion between those two. So just make sure you're happy and practice knowing that you've got a bit which has got either a 0 or a 1. It's got 2 states, then you've got 4 states, then you've got 8 states. Okay, 2, 4, 8, 16, 32. Does that ring a bell? Because of course that's binary, isn't it? Good. Okay, so those are the units of data storage capacity. There will be a 1 or maybe 2 mark question in there on that. They'll begin by asking you something about why do computers use binary, and you can talk about the fact that computers are made of transistors and circuits which have got 2 states, on and off, and that's easily represented in binary with 2 states. And then we've got the units of data storage capacity, bits, nibbles, bytes, and the rest I reckon pretty straightforward. Okay, so let's now go in with a little bit more detail on binary. We know that binary uses 0s and 1s. And of course, denary, which is our number system, uses 0s to 9s. And then you've got hexadecimal, which goes from 0 to 9 and then goes A, B, C, D, E, F. And you can see A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And I find the biggest challenge when sort of trying to teach students about hexadecimal is that, for example, if they write down 1, 0 in hexadecimal, students will say, well, that's 15. No, F is 15. What's the next place you go to after 15? It's 16, and 16 doesn't exist because that's a 1. So 1, 0 would be 16. So whatever that first digit is, you're fundamentally going to be multiplying it by 16. So if it's, say, for example, 1C, it's going to be a 16, and then it's going to be a 12. Okay, so thinking about how hex works. But we'll go into that in a bit more detail shortly. Right, the next step is binary conversions. I think that the hardest part of doing conversions to binary, and by the way, on the top left there, can you see that I've said convert this number, and see that little 2 there? That 2 is to tell you that this is a binary number, all right? So that 2 tells you it's a binary number. All right, good. So we're going to convert 10, 10, 10, a binary number, into denary, which is our number system, which goes from 0 to 9. Okay, the biggest challenge that you have to do is draw out this grid, which you can see on the board. So many ways to mess this up, although it looks quite straightforward. Is the first thing you need to think about the if you're writing in Arabic, you don't write from left to right like in English. You write from right to left. So this grid goes from right to left. So it starts on the extreme right hand side with 1. And then all you've got to do is double the number as you go along. So 1, 2, 4, 8, 16, 32, 64, 128. And it won't go beyond 128, by the way. So as long as you are able to double your numbers and write out the grid, this thing is almost foolproof. Okay, so you've been asked to do this conversion. You've written out the grid like so, and you've got time to do it. So just focus on what you absolutely have to do on your system. So draw the grid out. Next thing is drop the numbers that you need to convert into the grid. So far, all we've done is taken 10, 10, 10, 10, and dropped it into the right places on our grid. And then we've got these sort of seemingly random numbers above, but of course they're not random at all. They're going to help us work out what this is in our own number system, which counts from 0 to 9, from 0 to 9. So what you have to do then is do some maths. So just to recap, we've simply dropped our number that we're going to convert from binary to denary into this grid. And you can see that above our binary numbers, you've got what I'm going to call the grid numbers. That's the 1, 2, 8, 64, 32. And all you have to do is ask yourself the question, which of my numbers, which of my grid numbers, 1, 2, 8, 64, 32, the top line, which of those has got a 1 beneath it? Because those are the only ones you're going to worry about. So for example, there's 128, there's 132, there's 18, and there's 12. So all you've got to do is do a quick maths and add those together. And where there's a 0, you don't need to worry about it. So we're not going to try adding 64, we're not going to add 16, and we're not going to add 4 or 1, but we are going to add 128 to 32, and then we're going to add 8, and then we're going to add 2. Well, 8 and 2 is 10, and 32 makes 42, and let's see if your maths gets there any quicker than me, but hopefully this is making sense to you, and you end up with 170. Easy peasy, isn't it? So that's all that you need to really worry about in terms of the maths that you're doing. So that is converting from a binary number into a denary number. A bit of simple addition, okay? Very, very straightforward. So I'm going at pace now. And I find that generally students doing computer science, their numbers are pretty good. They might not be the best mathematicians on earth, but their maths is more than good enough to cope with this. So hopefully that's you. All right, the next one. We're now going to convert the number 170. You see the little 10 I've put there? That 10 means this is a denary number, a base 10 number. So we're going to take that number and we're going to convert it into binary. Okay, so that is our job. So we're going to have to go from binary to denary and from denary to binary. So then you've got to ask yourself the question. So we are looking to convert 170 into a denary, 170 into a binary number. So you draw the grid out exactly the same as before, and you ask yourself this question. What is the largest grid number? And the grid numbers are 1 to 8, 64, 32, 16, and so on. Those are our grid numbers. What's the largest grid number that goes into our number once? Well, it's 128. 128 goes into 170 once, and there's a remainder, or a modulus as it's called in computer science terms. So guess what? Because it goes in once, all you have to do is write down a 1, and then you've got to do some maths, and you've got to work out what the modulus, what the remainder is, okay? So 128 goes into 170 once, and there's 42 left over. Now, this is like rinse and repeat, really. You ask yourself the same question. We've got a leftover of 42, see there on the bottom right-hand side, and the question is, what is the largest grid number that goes once into 42? And of course, the answer is 32. 32 goes into 42 once, and you've got 10 left over. And we ask ourselves the same question again. And of course, 8 is the largest number. 16 is too big, so 8 will go into 10 once, and that's going to give us a leftover of 2. And there is a 2 there, so we can pick this 2 there. 2 goes in once, so let's pop a 1 underneath that one. And that is our number resolved. And now we get to the really hard part, is that anywhere where you've not written a 1, guess what you do? Yeah, you were ahead of me. You put a 0 there. So that is a really easy way of converting 170, which is a denary number, into our binary number, which is 10101010. Good. So that is the first stage of our conversion done. We've gone from binary to denary, and then we've gone from denary to binary. And all you have to do, guys, is just draw out the grid. It is no more or less complicated than that. All right, the next job is we're going to look at hexadecimal conversions, okay? Now, you may not want to do this, but I actually think it's incredibly useful to actually spend a few minutes just looking at these binary numbers. And after about 2 or 3 minutes, whoops, let's go back to where I was. After about 2 or 3 minutes, you will realize pretty quickly that binary numbers, they actually make complete sense. We've been taught at primary school to count from 0 to 9 and then to say 10 or 10 as is written down. But actually, it took a lot of effort to get you to do that. If you look at binary, you can see that the right-hand number changes each time. 0, 1, 1, 0, 1, 1. Look at that right-hand number. It changes every single time, okay? And there's actually a logic to that, and it's probably worth spending a few minutes just looking at counting from 0 to 20 in binary. And once you sort of see how the system works, it's really straightforward, but it just takes a little bit of time to do that. But it might be useful for you to sort of build a bit of confidence. And I reckon about 2 or 3 minutes, and you'll find that you can count to 20 or 30 or 40. You get no extra marks for it, but it's really useful to have the confidence to do that, because you are going to have to be able to count to 3 when we do the arithmetic. Okay, when we do addition. Sorry, you're going to need to count to 3. Okay, So we're now going to look at hex conversions. Now hex conversions are a little bit more complex in as much as there's an extra step. So denary to binary and binary to denary, which we've already looked at, there's just one step. We draw the grid and then we either ask ourselves what's the biggest grid number that goes in once and do the remainder, or we simply go through it and we do some simple addition. But if you want to go from denary, our 0 to 9 system, to hex, you've got to go through binary. And equally, if you want to go from hex through to denary, you need to do exactly the same thing. You've got to go through the binary conversion. So you're always going to be doing something of what you've done before, but there'll be an extra step when it means turning things into hexadecimal. However, those extra steps are actually really, really straightforward. And in fact, you've already done them. So we talked a little bit earlier about a bit, and then we talked about a nibble, and then we talked about a byte, okay? And if you remember, a nibble is 4 bits. Well, in front of you, you have got 2 nibble tables. Got to be careful how you say that. You've got 2 nibble tables, and they're typically going to give you one number with 2 digits, okay? And they'll say convert this into denary. So 5F is a hexadecimal number. We've got the 5 and we've got the F. The easy way you can work this out is by thinking, well, it's 5 times 16 plus whatever F is, which is 15, and then you can just do the maths. But this is the way you can work it out to be absolutely sure, okay? So you draw out your 2 nibble tables, 1, 2, 4, 8 and 1, 2, 4, 8. Now, once you've written both of those out, you then do what you've done before, is you ask yourself the question. And I'm going to start here with the 5. If we look at the 5, we can ask ourselves the question, what is the biggest grid number that goes into 5 once? And of course the answer is 4. 4 goes in once, so we draw a 1 down here, and then we've got a leftover of 1, and 1 goes in once, and we've resolved. Because you do need to know that, we'll come on to what you need to know next, which is the F. You do need to know that F is 15, and it isn't that hard because obviously you've got A, B, C, D, E, F. 10, 11, 12, 13, 14, 15. So it's not that much to learn, but there's no G. That would be a mistake. Then let's resolve the F now. We start with F. What's the biggest number that goes in? It's 8. We've then got a 4. We've then got a 2. And then we've got a 1. Because look, 8 and 4 is 12, 13, 14, 15. So these all add up to 15. So it's all the ones. So therefore, we have now done the first part of this, which is we've created 2 nibble tables. And now we need to smash these 2 nibble tables together a bit like so. And then we're on the home straight. We're doing exactly what we've done before. And we simply go through it and we do the addition. So we know that we can ignore the grid numbers, these guys, when it is a 0 down there. But if there's a 1, we need to take that a bit more seriously. So all we have to do is take our 64, add that to 16, add that to 8, add that to 4, add that to 2, and I'm guessing the good mathematicians are already ahead of me here because you should have got to 95. So that is your hexadecimal conversion. And like I said, the other way of doing this that is really, really easy is to simply think, well, it's a 5 and it's an F, and that's going to be 5 times 16 plus whatever the value of F is, which fundamentally will also give you 95, all right? So that is the step that you need to understand there. All right, so the next thing we're going to look at now is binary addition. This is adding up binary numbers. Now, this is very, very straightforward, and there's, I guess, a couple of things that you need to know. The first thing is that 0 plus 0, wait for it, is 0. 0 plus 1, I think you're ahead of me, is 1. 1 plus 0 is 0. 1 plus 0 is 1. But here's the difficult one. 1 plus 1 is 1, 0. And 1 plus 1 plus 1 is 1, 1. So you are going to need to be able to count to 3 or 4 in binary in order to be able to do the binary addition. So let's have a look at an example as we go through and see if we can get this working. So here's the example. We're going to take the first line, which is 1101, 1010, and we're going to add it to 0100, 1010. And we're going to start at the right-hand side. And the first question is, what is 0 plus 0? And we know that the answer is 0 plus 0 gives us 0. That is so massive, it's ridiculous. And then we've got the next line, which is 1 plus 1, which is 1, 0. You see down here, there's my 1, and there's my 0. 0 plus 0 is 0, plus the 1 we carried gives us 1. 1 plus 1, I'm here now, 1 plus 1, there we go, no good saying here, there we go. 1 plus 1 is 1, 0. 0 down, carry the 1. 1 plus 1 is 1, 0. 0 down, carry the 1. And then we just keep following it through, okay? 1, 1, 1, 1, 0. And there we go. So literally, if you look over here on the left-hand side, this bit of maths here is the only thing that you really need to know to complete these binary additions. You need to know that 1 plus 1 is 1, 0, and that 1 plus 1 plus 1 is 1, 1. There's a lot of ones in what I'm saying, I can hear that. But those are the only areas in which you can possibly get this wrong. So just make sure you're happy that 1 plus 1 is 1, 0, and 1 plus 1 plus 1 is 1, 1. I'm going to not say 1 for a while. I think we'll just leave that there. My advice to you would be to go onto, to have a go at a few of these, because there are loads of binary calculators online, and I would set yourself a couple of additions and then just check your answers to make sure you're doing it right. But fundamentally, as long as you remember that 1 plus 0 is 1, and that 1 plus 1 is 1, 0, and 1 plus 1 plus 1 is 1, 1, nothing else can go wrong. But it's easy to make a mistake with it, so just go through it deliberately. Okay, where are we at? We're at 21 minutes in, and we are making good progress here. The next thing are binary shifts. Now, binary shifts are a very simple way for CPUs to be able to do calculations in terms of division and multiplication. Right? It's not the most accurate way of doing it, as you will see in a minute, but it's called binary shifts, and this is how it works. And you should have figured out now that this sort of set of numbers we've got here, over here, this looks a little bit like the table we drew out, except it's the other way around, isn't it? So rather it's 2, 4, 8, 16, 32, 64. What's exactly the same is that it's doubling each time. Or, if you're going from right to left, it's halving each time, okay? So what you need to understand is that there's a very quick way for the CPU to be able to multiply and divide binary numbers by using this system called binary shifts. And each shift is regarded as being a 1-place shift, a 2-place shift, you see down here, a 3-place shift, a 4-place shift, a 5-place shift, and so on. So they might ask you to perform a 4-place binary shift on a certain number. But they're going to ask you to do it left or to do it right. In other words, they're going to ask you to double the number or to halve the number. But they could ask you to double the number twice, or 3 times, or 4 times, or they could ask you to halve the number 3 or 4 times. All right? So, for example, if we went from this 4 here and we did a 1-place binary shift left, you're going to end up here. If we went to our 4 again, we started back here again, and we did a 2-place shift right, we go 1 place, and we go 2 places, all right? So that's kind of the fundamentals of binary shifts, that it's a very quick way of both dividing and multiplying at speed. And when they talk about places, they're talking about how many times you're dividing it by itself or multiplying it by itself, okay? So let's have a look at this in a bit more detail. So we've got... we'll look first of all at binary shift left. So you've got a binary shift left and a binary shift right. I tend to remember this, my way of remembering it is that it's the monarch's right to divide. So whether you want to go for a king or a queen or a prince or a princess, you can pick your flavour. But I remember just the term, it's my right to divide the people. Right to divide. So as long as you remember that you go right to divide and then it's left to multiply or to double, that's all you need to worry about. So let's have a look now at binary shift towards the left. So don't forget, if it's right to divide, it's left to multiply. So we know that we're multiplying each time that we do it. If we go 1 place, we're doubling it. If we go 2 places, we're doubling it again. 3 places, doubling it again, and so on and so forth. So can you see here, if we take this binary number 1100 and we perform a binary shift one place left, what happens is 1100 becomes 11000, so an extra 0 gets added. This is so simple, isn't it? If we went 2 places, we add 2 zeros. If we go 3 places, we add 3 zeros. So all you're doing fundamentally is sticking more zeros on the end of a number. That's all you have to do for these binary shifts, okay? It's really quite straightforward. So that is how a binary shift left works. And all you're doing is doubling, 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 doubling. Okay, you're simply making the number bigger and bigger and bigger and bigger and bigger. That's how it works. So that is your binary shift left. Okay, let's look at the other way now. And this is where you get this slightly odd thing, is that binary shift right to divide. So the number's getting smaller. And bear in mind, now we're going from left to right because this is binary shift right. So let's start off with this number. They might give you this number and they will say, perform a binary shift one place right on this number. And you can see what happens. We've got 100100. And what's happened is that actually, I've not shown it here, but there's in fact a 0 that's drawn in here. It looks like an orange donut, but it's a 0, trust me. So you actually lose a 0 from the end. You get rid of this 0 here, that's deleted, and you simply move it, or you put a 0 in front of it. So rather than being 100100, it becomes 010010. And of course, this first 0 has no impact, but taking off the last one does have an impact. Well, it does have an impact. It makes the number smaller. But you can see each time you are halving the number. Now, if you've worked through this number set you can see in front of you, you will see there's a problem when we get down to around about here. Okay? And that's because you start to lose accuracy at this point. Okay? So really, this doesn't work because you're losing your accuracy. The value should be 4.5, but it's not. And if you follow it through, you actually lose a degree of accuracy when you perform binary shifts right, because you're losing some of the detail. And of course, the detail you're losing, let me just get rid of this here. The detail you're losing is that you've been dropping numbers off the end. When you're dropping a 0 off the end, that's fine. Dropping a 0 off the end, that's fine. But when you're actually losing a 1, this 1 here, well, you can't replace that with a 0 because it's not going to be accurate. So it's a fairly rough and ready way to actually divide a number. So again, I would personally think about it in these terms. That first of all, get clear in your head that it's right to divide and it's left to multiply. And that whether you're going 1 place, 2 places, 3 places or 4 places, you're either doubling or halving it each time. So let's say, for example, you take the number 4. If you're going to double it, you go to 8. If you're going to halve it, you go to 2. If you're going to halve it again, you go to 1. And each time you halve it or double it, that is 1 place. So as long as you're happy with the difference between left and right, and then it's right to multiply and it's left to divide, that should be a nice, easy way for you to earn a few extra marks on your paper. And again, this is written out in case you find this a bit easier to understand, but we've got the right shift, which is division. So what do? You discard the rightmost bit, and then the remaining bits you move 1 place to the right, and you fill the empty place on the left with a 0. And fundamentally, the left shift is completely the same, except you're going left instead, and you're moving the bits to the other side. So this time, the leftmost bit is discarded, and the remaining bits move 1 place to the left, okay? So have a little practice of that. Ask your teacher for some past paper questions. Have a crack few of them. Have a go at a few of them, because you will find that the binary and the hex and the shifts are areas that you just absolutely must score full marks on, because there's going to be possibly 3, 4, 5 marks from this. So it's really important to make sure that you pick up this low-hanging fruit and actually get your due credit for those types of questions. Okay. Bear in mind, if you've got any questions for me, please put them in the comments. Okay, because I'm more than happy to go back and look at anything. All right. Now we're on to the last stretch. We've done half an hour. We've moved really quite quickly through this, and I'm hoping that's made some kind of sense to you. We're now going to look at character sets. Now, the first thing that, and in fact, I'm going to go forward one slide because I think bizarrely I put it here. No, I didn't put it here. Where did I put it? Bear with me a second. No, I didn't. Okay. So in that case, what I need to say to you is that, oh, there we go. I've got it here. I knew that there was some common sense somewhere. Let me try and draw this for you. There you go. This particular statement here is, there's a, I would say, a 60 to 70% chance, he says, making a random number up, that this will appear in your exam. Because if they ask you about character sets, they're going to ask you what is a character set. And so your first mark is to say it's a set of characters the computer can understand. That particular phrase has appeared in countless mark schemes. I have an issue with the word understand, but let's not go into that now. But a character set is fundamentally a set of characters that the computer can understand. So there's your first mark. If you think about this from a more abstract point of view, when you press a key on your keyboard, for example, the A key, the Q key, the space bar, there has to somewhere be a table that tells the CPU what that character actually is. Otherwise, it's just a random character, isn't it? So fundamentally, there's a lookup table, and that lookup table is called either ASCII or Unicode. So it means that every single key that you press on your keyboard has an equivalent binary number, and there it is again. Every key that you press on your keyboard has got an equivalent binary number. So, for example, S might be 000100010. It's not, but it could be, okay? But each number, each letter on your keyboard, whether it's a spacebar, a letter, an alphanumeric, whatever it is, it's got its own unique binary number. And that's how a character set works. Now, you've got two flavors, two types of character sets. You've got ASCII and Unicode. Thank you, dog. So the first thing it's going to ask you is, what is a character set? And you're going to say it's a set of characters the computer can understand. It's then going to try to get out of you what the difference is between ASCII and Unicode. And this works a little bit like this. Well, ASCII is an 8-bit number set, okay? There are only 8 bits in an ASCII, for ASCII, which means that if you took 1 byte per character, okay, don't forget we've got bits, we've got nibbles, and we've got bytes. So if you took 1 byte, which is 8 bits per character, that means that ASCII can represent up to 256 characters, which is fine if you are writing all of your articles in English. So by the time that you've gone through the capital A to Z, the lowercase A to Z, 0 to 9, the tab key, the space bar, the comma, punctuation, escape key, all that sort of stuff, you still don't get to 256 characters. So if you're writing in English, ASCII is absolutely perfect. But the problem is, people don't write in English. They write in hundreds of different languages. And of course, 256 characters or 256 possible slots is not enough when it comes to Chinese, Japanese, Russian, Greek, German, French, etc., 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 which have got their own particular characters, and in fact several different sets of alphabets. Simply 256 characters isn't enough to represent all of those characters. So therefore, they invented something called Unicode. And you can see from the graphic in front of you that Unicode is simply a larger character set. You can represent more characters. So this time, rather than being an 8-bit number that would give you up to 256 characters, this is a 32-bit number. Okay, so 8, 16, 32. That would be a 2-bit shift, wouldn't it? There we go. So it's a 32-bit number which can represent over 4 million characters at 4 bytes per character. Now, I'm going to make a prediction here that I think they might get you to do some maths around ASCII and Unicode. But for you to be successful with that, the maths itself won't be hard, but you would have to know that ASCII is an 8-bit number, it's an 8-bit number character set. Within that character set, it represents, each character is represented by 1 byte. You'd also need to know that Unicode, as a 32-bit number set, is represented with 4 bytes per character. So there's 4 times the number of bytes per character represented in Unicode than there is in ASCII. But of course, Unicode, with 4 million characters, has got enough characters to represent all the languages in the world, a couple of times. So there's going to be no need to ever change that. But ASCII was only really good for English and a few French and German, sort of, the SZ and the accent aigu and grave and so on. So it's only good for those. But Unicode is just good for everything. So Unicode is the one that's generally preferred because it's universal in a way that ASCII isn't. So they might ask you, why would it be necessary to use the Unicode character set? And you would simply say, because the ASCII character set can only represent up to 256 characters, and there are more characters than that in all the languages in the world. Whereas Unicode can represent 4 million characters, which means that every single character in every single language on Earth can be represented using Unicode. There we go. So that's your character set. And I would recommend actually going away and doing a bit of learning around this stuff here in terms of 1 byte per character and 4 bytes per character. I think that might be useful because they could get you to do some maths on that. Talking of which, and I guess this will be the last thing really, is that if they do ask you to work out the size of a text file, this is how you would do it. And you need to know 2 things. You need to know how many bits per character. In other words, you need to know which character set. And just whizzing back here for 1 second. And we know that ASCII is 1 byte per character. And we know that Unicode is 4 bytes per character. So you're going to have that inside your head. So you're either going to be multiplying by 1 or by 4. But you need to know how many characters there are. So if there's 300 characters, you're then going to take your 300 and you're going to multiply it either by 1 or by 4, which will give you an answer in bytes, depending upon whether it's ASCII or Unicode, and that will give you your answer. Now, the reason I'm being a bit bold with the prediction here is that this has been in the syllabus for a couple of years. They've never actually asked anyone to do this yet, so I've got a suspicion they might have a little go at this in your exam. All right, so that is the ASCII versus Unicode, but just sort of important takeaways there for you are that you've got the fact that it's a set of characters the computer can understand. There's a definite mark for you there, and then they might talk to you about why you would use ASCII rather than Unicode. Okay, so those are the key areas to focus on there. And what I'm going to do before I go is just really, really quickly run through this again. And I know there are a couple of you online. I know you had your mock today, so you've done really, really well to get this far. But if you've got any questions or any parts of this that make no sense, just shout in the comments and I can pause and run through it really, really quickly. Well, we talked first of all about the fact that when it comes to numbers, that computers can only use binary. That's where this all started, wasn't it? And the question is, why is it that computers can only use binary? Well, it's because computers are made of circuit boards, and circuit boards only have 2 states. One is on and one is off, okay? And we're almost back to the start again, aren't we? One is on and one is off, and that is how a computer, and that can be easily represented, there we go, that can be easily represented in binary as 1 being on and 0 being off. So there's your first mark. The second thing is make sure you know you've got bit, nibble, byte, and then the order in which the rest of these go. Sometimes they ask you just to order them in terms of size, biggest to smallest, smallest to biggest, and sometimes they'll get you to do some conversion from bytes to kilobytes or megabytes to nibbles, that sort of thing. And it often is just the thousands you've got to multiply it in, so it's not too bad. But you've got to be clear, and you might find it useful to have a look at this and then just write it out. If there are 1, 2, 3, 4, 5, 6, 7, 8, I think 1, 2, 3, 4, 5, 8. So 8 different units you need to know, and make sure you can A, put them in the right order, and you know how many bytes or kilobytes or megabytes is in each one. All right. We then looked at hex versus binary and denary. Hex counts up to 15, which is your F. And then once you get to 1, 0, that's 116 and no units. Okay. And we talked about denary, which goes 0 to 9, which you are aware of. We then looked at converting from binary to denary. We said draw the table, drop your number in, and then do some simple maths. If there's a 1, you're going to then look up and take your grid number, and you're going to add that to the next place there's a 1, which is this one here, and then so on and so forth. So that is how you do your binary conversion. And then we did that one, we did that one, and then we went through and did our conversion from denary to binary, and we asked ourselves the question, what is our biggest number on the grid that goes into the number we're looking to convert once? If it goes in once, you write a 1 there, and then you've got to work out the remainder, and then you just rinse and repeat and go through that time and time again. You will end up with a bunch of 1s written down, and once you've resolved your number, you then drop in zeros, and there is your number. We looked at hex, and we talked about the fact you've got to go through binary conversion as well. And we said for hex, you can either, with the 5f in front of you, say that it's 5 times 16 plus the value of f, which is 15, and work it out. Or you can draw 2 nibble tables and work it out as we did before, bash them together, and then do the maths as we did before. All right. Then we'll look at binary addition. Really, it's addition, which you start on the right-hand side as you do normally, and you've just got to know those 3 key facts, isn't it? That 1 plus 0 is 1, that 1 plus 1 is 1, 0, and that 1 plus 1 plus 1 is 1, 1. And it's those 3 ideas you've got on the left-hand side there. We then looked at binary shifts, and we talked about a binary shift is either halving or doubling a number. 1 shift halves it, 2 shifts, halves it again, 3 shifts, halves it again. So it's a question of whether you're halving or doubling it. And the way to remember this is that it's right shift to divide and it's left shift to multiply. Okay, and the number will get bigger. And it's really just a question of either adding or losing numbers from the front or the back of the binary number you're working with. Okay. After that, we looked at character sets. There's your answer for the first mark or on May, or whatever it is. It's a set of characters the computer can understand, and we talked about the 2 flavors, ASCII and Unicode, one which is 1 byte per character, one which is 4 bytes per character, and that one can represent all the characters, all the alphabets on planet Earth, and one can't. All right? So that is it. Now, I've got a feeling that you're going to be way too shy to answer any quiz questions, but let me put this on there and see if anyone is brave enough to get involved. So this is question 1. Doing a logical shift left, can you remember my mnemonic? There's 2 hard words for me to say. Can you remember my mnemonic, which was how this works? So doing a logical shift left does what to a binary number? That is the key question. I never got my camera working, which is very irritating. Oh, we have got an answer. Look at that. Well done. Who's behind the door? You were excellent last week, so congratulations. And you are absolutely correct. What about this one? Let me give you a wonderful sound. You can have some applause for all that good work. What about this? Doing a 2-bit left logical shift has what effect? So what do we think about this? Okay, so dividing it by 2, and obviously dividing it by 2, dividing it by 4, we're halving it, and multiplying it. So I hope that kind of makes sense. So what do we think? Doing a 2-bit left logical shift has what impact on a number? What do we think? Who's behind the door? No pressure, but I think it's just you. Ooh, we've got a C, and then we've got a bit of questioning with no, it might not be a C. Should we go with your C and see? Oh, he's come again. Or she's come again. It's a D, or they've come again. It's a D. What do we think? You were right. It was a D. So well done. You corrected yourself. Well spotted. It's quite difficult to get your head around, but I just find it easier to start with, in terms of is it am I multiplying, am I dividing? And then just think about, am I halving, am I doubling, etc. Now, this one I think is wrong, actually, because I'm going to go on to this one instead. Okay. What about this one? C9 to binary. Oh, this will be quite hard for you to work out. That'll be quite difficult for you to do, but let's see if you can do it. If you convert the hex number C9 to binary, what do you end up with? And again, this would be 2 nibble tables, wouldn't it? So thinking about A is 10, B is 11, C is 12. What do you think that would be? Is it A, B, C, or D? Who's behind the door? It's a bit of quick maths for you to do here, but I've got complete faith in you. What do you reckon? What's the answer to this one? Convert the hex number C9 to binary. What do you think? You have said A. Let's have a look and see what we did there. That was very, very good. I was trying to fiddle with my camera, still can't make it work. Just randomly stopped working. Well done. That is outstanding. Well done. That was very good indeed. You have the organ for that. We have a ding as well. Absolutely outstanding. Right, let's do a few more. State the deanery representation, which is a pretty ridiculous way of asking the question. State the deanery representation. So what is 00111101 in deanery? Can you figure it out? 00111101. What do you reckon? Ooh, we have a new customer. Sanoixen. That's a good Sanoixen. Okay, that's good. I like that. Nice icon there as well. That's very good. A nice avatar. Nice picture, actually. Decent sunset. And you have said A. I got carried away there. Oh, you were close. It was B. It was B, but I like it. We're going to give you some thunder because that was an impressive effort. Okay, what about this one? What letters does hex use? You kind of need to know this, or else the whole of the hex thing is a complete blowout. Yeah, who's behind the door? You were spot on. That was very impressive indeed. What letters does hex use? Is it A to E, A to G, A to F, or A to D? What do we think about that? A to E, A to G, A to F, or A to D? If you can hear whining going on, by the way, it's not me. It's a dog who wants attention. He will get it shortly. Don't encourage him. Oh, yeah, I can see we've got, I can see that who's behind the door has come in with a C. So let's have a quick check of that. Well done. You are absolutely spot on. You're good at this. That's very good. Let's make something a bit harder for you. I've got anything nastier for you. Oh, this is a bit nastier. Convert this binary number 10101010 to hex. There's a possibility, of them taking some of this hex and binary stuff, converting it in and mixing it somehow in with something on text and characters. I do fancy they might have a go at this time. So what do we think? Convert the binary number 10101010 to hex. Let's have a look. I'm sure who's behind the door's come an answer here. Who's behind the door? No, B, C. No, not yet. Still figuring it out. Ooh, we have AA. Let us see if you are a success. Yes, of course you are. That was really good. Well done. That was super quick as well. You are in hexadecimal heaven. Okay, I'm impressed. I think you've kind of got all of that. Binary shifts. Make sure you're happy with those. This is what I would think about for next time. Have a little practice of conversions with units, file sizes, binary, hex. Make sure you can do it both ways. Make sure you practice different conversions each time. Make sure you've got your 2 marker on why binary, why do computers use binary. And while we're at it, make sure that you know what a character set is and why you would want to use Unicode rather than ASCII, even though it requires more space, more memory. Learn effect versus perform. Yeah, that's one I've not mentioned actually. And this is important. Let's try if I can highlight this. Is that going to highlight here? I've got a whiny dog. Learn effect versus perform. So they might say, what would the effect be of performing? What would the effect be of doing a binary shift? And so in other words, it would halve the number or it would double the number. That would be the effect. Whereas perform a binary shift is just sort of do the maths. Who's behind the door? You are very, very welcome. I'm hoping, out of interest, who's behind the door and Sanoxniz, how much of this was, I guess what I'm looking for, was there anything here that was new, or is understood better, and so what if anything were the areas that you found slightly trickier, or does this just confirm that you've got amazing teachers and that you are in a good place? Where are you with that? What was new today, I guess? Learning the fixed size of storage medium, I put that in there because, again, it is in the specification that they do expect you to know that, for example, you might use a DVD to hold a film, but you couldn't use a DVD to back up a whole catalogue of films because there's just not enough space. So there's a possibility, or for example, that a compact disc, a CD, would be good for an album's worth of music, but it wouldn't be good for backing up, images, because there just wouldn't be enough space. So there's that sense of needing to know sort of which types of media and medium carry, what they can hold. Okay, then we've got learning the steps of binary addition, which we did. Revise those CPU registers. Make sure you're happy with all those registers and that you know them all, and then just start doing your revision, guys. It's been an absolute pleasure. I will leave it there. What have we done? We've done 6:30 or 7:20. So yeah, we've done really, really well. Okay, thank you so much for that. I was solid but amazing recap. Good. Well, do you know what? If all that I did for you was to help recap that stuff, then that is also brilliant, because that's a really useful way to spend your time. So thank you so much for coming. I will see you same time next week, hopefully with my lungs feeling a bit better. And we'll move on to the next topic. Have a really good week, and I hope your mocks went well. See you guys. See you next time. Bye-bye. Bye-bye.